So bio applications. So basically here we've got 4 different categories, I think. So this is high resolution imaging. And the first thing you'll notice compared to some of the material slides that John was showing is the spring constant. So in the next 4 slides, almost all of these spring constant, I'm sure, are less than 1 Newton per meter, because the samples are going to be sort of very soft and delicate. So we have a couple of different probe choices here for high resolution imaging. Again, you'll see for high resolution, the end radius is 1 to 2 nanometers typically. And if you look at some of the images along the bottom, this is the types of sample we'll be looking at here. So origami DNAs, plasmid DNAs, it could be proteins, viruses, various different biomolecules. Scan sizes, as you can kind of see by the scale bar, this is typically less than a micron. It's pretty common to have a 512 nanometer image and image at a pixel density of 512 by 512 and those kind of ratios. So these probes are all very good for those applications. We've got the peak force high res F-A. By the way, I hope you're getting used to some of the probe naming jargon. So yeah, the high res there, HIRS, specifies high res. Most of these are used in peak force tapping because pretty much we're working in liquid now all the time. And so it does benefit using that peak force tapping technique where you don't need to tune the probe. We can control the amplitude and very low forces. So again, sort of image those delicate samples very nicely. Okay, I'm gonna move on to the next slide. So now kind of going up in scale quite a lot. So we've gone from the very small now to probably maximizing the scan range on your AFM. So if we're looking at cells, which could be bacteria cells, yeast cells, fungi, mammalian cells, you could in fact use a full 100 micron scan size or even larger. So resolution and good resolution for these samples might be a lot different on the previous slide. So you kind of see here the end radius for these probes called out, 70 nanometers, 20 to 60 nanometers. That is good enough because again, you'll see the features that you want to see. But also with scan sizes this large, and again, if you have 512 pixels or 1024 pixels, you're not going to see anything, less than that anyway. A pixel could be 100 nanometers or more. So you don't really need a probe radius very sharp. The other thing is, of course, as well, it's not the best analogy, but I always tell people, a cell is like a balloon filled with water, right? So if you're using a very sharp needle, you definitely don't want to sort of poke it and poke through it. So those probe end radii that are around 70 nanometer is perfect. Low spring constants again, and typically using kind of peak force tapping techniques. So just to comment on the individual probes, the first one here, the peak force quantitative nanomechanics live cell A calibration. That's the naming convention there. We call them the live cell probe. Again, this is a very unique probe. It has a very tall tip. That actually prevents an artifact that some of you may have experienced in the past, where if you don't have a tall tip shank, you can actually get like a shadowing effect or an artifact where as you kind of image over a tall object, the cantilever can interfere with the sample. So if you have a very tall tip shank, you don't get that problem. So this is a very nice probe, a tall tip, a defined end radius that can be SEM inspected. And again, this can be a laser Doppler vibrometer calibrated so that you're not working with a nominal value. The spring constant is exact for each type of probe. Scan-assist fluid probes and other types of probe. I'll say a little bit about the MLCT here. It's kind of hiding behind my go-to panel. So John mentioned this at some point earlier, and we actually had a few questions I noticed as well about drift and sort of probe bending. So I'll go through that again quickly. So these drift compensated probes, a lot of like the low spring constant probes, they have backside coatings full. So then you can be liable to a bimetallic effect. So most things kind of expand or contract when they change temperature and at different rates. So if you have silicon nitride and then a metal layer on top, and then you put that in fluid, or you put a laser spot on top that could heat it up, or you're actually using heating and cooling accessories, they will change temperature and expand or contract at a different rate, and that will tend to, like, you know, flex the cantilever one way or another. So most people, and again, I experienced this doing my PhD, would just kind of let it settle, and it'll bend a little bit, and you kind of wait for the photodetector spot to stop moving, and then you'll do your experiment. But we can now actually design to get around that problem completely by just having this metal coating right at the end. So where you put the laser spot, so you still get the reflectivity and signal increase, but it's not enough metal to actually kind of flex the probe, so you don't drift so much. Okay, next slide. So high-speed imaging. Again, this is a little bit analogous to John's material slides on high-speed imaging.